The ancient Romans were masters of engineering, constructing vast networks of roads, aqueducts, ports, and massive buildings whose remains have survived for 2 millennia. Many of these structures were built with concrete. Rome's famed Pantheon, which has the world's largest unreinforced concrete dome and was dedicated in 128 CE, is still intact, and some ancient Roman aqueducts still deliver water to Rome today. Meanwhile, many modern concrete structures have crumbled after a few decades. Researchers have spent decades trying to figure out the secret of this ultra-durable ancient construction material, particularly in structures that endured especially harsh conditions, such as docks, sewers, and seawalls, or those constructed in seismically active locations. Now, a team of investigators from MIT, Harvard University, and laboratories in Italy and Switzerland has made progress in this field, discovering ancient concrete manufacturing strategies that incorporated several key self-healing functionalities. For many years, researchers have assumed that the key to the ancient concrete's durability was based on one ingredient: pozzolanic material, such as volcanic ash from the area of Pozzuoli on the Bay of Naples. This specific kind of ash was even shipped all across the vast Roman Empire to be used in construction, and was described as a key ingredient for concrete in accounts by architects and historians at the time. Under closer examination, these ancient samples also contain small, distinctive millimeter-scale, bright white mineral features, which have been long recognized as a ubiquitous component of Roman concretes. These white chunks, often referred to as limeclasts, originate from lime, another key component of the ancient concrete mix. These are not found in modern concrete formulations. So why are they present in these ancient materials? Previously disregarded as merely evidence of sloppy mixing practices or poor quality raw materials. The new study suggests that these tiny limeclasts gave the concrete a previously unrecognized self-healing capability. If the Romans put so much effort into making an outstanding construction material, following all of the detailed recipes that had been optimized over the course of many centuries, why would they put so little effort into ensuring the production of a well-mixed final product? There has to be more to this story. Upon further characterization of these limeclasts, using high-resolution multi-scale imaging and chemical mapping techniques pioneered in research lab, the researchers gained new insights into the potential functionality of these limeclasts. Historically, it had been assumed that when lime was incorporated into Roman concrete, it was first combined with water to form a highly reactive paste-like material in a process known as slaking. But this process alone could not account for the presence of the limeclasts. Studying samples of this ancient concrete, researchers determined that the white inclusions were made out of various forms of calcium carbonate, and spectroscopic examination provided clues that these had been formed at extreme temperatures. As would be expected from the exothermic reaction produced by using quicklime instead of the slaked lime in the mixture, hot mixing was actually the key to the super durable nature. The benefits of hot mixing are twofold. First, when the overall concrete is heated to high temperatures, it allows chemistries that are not possible if you only used slaked lime, producing high-temperature associated compounds that would not otherwise form. Second, this increased temperature significantly reduces curing and setting times, since all the reactions are accelerated, allowing for much faster construction. During the hot mixing process, the limeclasts develop a characteristically brittle nanoparticulate architecture, creating an icily fractured and reactive calcium source, which could provide a critical self-healing functionality. As soon as tiny cracks start to form within the concrete, they can preferentially travel through the high surface area limeclasts. This material can then react with water, creating a calcium-saturated solution, which can recrystallize as calcium carbonate and quickly fill the crack, or react with pozzolanic materials to further strengthen the composite material. These reactions take place spontaneously, and therefore automatically heal the cracks before they spread. Previous support for this hypothesis was found through the examination of other Roman concrete samples that exhibited calcite-filled cracks. To prove that this was indeed the mechanism responsible for the durability of the Roman concrete, researchers produced samples of hot-mixed concrete that incorporated both ancient and modern formulations, deliberately cracked them, and then ran water through the cracks. Sure enough, within 2 weeks, the cracks had completely healed, and the water could no longer flow. An identical chunk of concrete, made without quicklime, never healed, and the water just kept flowing through the sample. As a result of these successful tests, the researchers is working to commercialize this modified cement material. Through the extended functional lifespan and the development of lighter-weight concrete forms, these efforts could help reduce the environmental impact of cement production, which currently accounts for about 8% of global greenhouse gas emissions, along with other new formulations, such as concrete, that can actually absorb carbon dioxide from the air. These improvements could help to reduce concrete's global climate impact, built 2,000 years ago, still teaching us today. Thanks for watching.